So, we have seen Bohr Sommerfeld model in last class. And we have seen that from Bohr model energy expression is mu z square e to the power 4 by 2 n square h cos square. So, here this n is principal quantum number, is quantum number 1, 2, 3, 4. Okay. And this was successful to explain the hydrogen atomic spectra, especially this series, Lyman series, Bohr series, then Paschen series, bracket series, Phone series, right. So, this in each series the separation between the spectral lines is decreased and it tends to the continuum or the it tends to the limit value of the spectral lines. After that it is continuous basically. And then so that this quantum number is 1 and this quantization of one parameter, that was angular momentum. And then Sommerfeld introduced the another quantum number, that is azimuthal quantum number, and using the special theory of relativity, this energy, if velocity of the particle is high, close to the light velocity, then one has to consider the special theory of relativity. Not it is then relativistic case, not non-relativistic anymore. So, this energy from Bohr Sommerfeld model or from extension of Bohr model by Sommerfeld. So, that En, its minus we introduced here just for convenience, 1 plus z square alpha square by n square, then it was n by k minus 3 by 4. So, now energy depends on two quantum condition and that gives two quantum number. So, n is a principal quantum number, and k is angular quantum number or azimuthal quantum number. So, this k value it takes, n value it takes 1, 2, 3, 4, and k value for a particular n is take 1, 2, 3 up to n. Okay. So, generally this principal quantum number. So, 1 it's cell and it gives names that we use name this K shell, L shell, M shell, N shell, etc. And now for each cell is now subdivided into subcell or this is also called orbit. So, each orbit is subdivided into orbitals. So, this name is given for k equal to 1 is given s orbitals, p orbitals, sp d, then 4 is basically f. Okay. So, these are the name we used for orbits and orbitals, and I have shown you that these people are in search of more quantization, because the spectral lines, hydrogen spectra, say whatever from Bohr theory, whatever we get that one line, say H alpha, H beta, H gamma, but it is not one line, it is more than one line, it is composed of more than one lines. And so people speculated that so we need more quantization, so there will be more energy energy levels, and corresponding from transition we will get more spectral lines. So, here we have seen that if I draw this for a hydrogen atom, so H alpha, so you know this n equal to 2 to n equal to 3. So, that is the transition is in Bohr series. So, now it was based on this. Now, if we use this energy, so this each energy level will be splitted. So, this n equal to 2, so k equal to 1 and 2. So, then it will be 2 lines, and I describe that energy generally is become its decrease, means become more negative. So, this one k equal to 1 and this one k equal to 2. Similarly, here it is 3 lines, 3 energy levels. So, k equal to 1, k equal to 2 and k equal to 3, right. And this, using this transition rule, del k selection rule, del k equal to plus minus 1, that I have shown you that that this transition is possible, and then 2 to 1 is possible, and 3 to 2 possible. So, actually we will get 3 lines, but experimentally it is found, experimentally it is seen that this spectral lines is composed of basically 5 lines, is composed of 5 lines, is composed of 5 lines. Okay. So, still the Bohr Sommerfeld theory, still it is not able to explain this experimental result, this called fine structure. So, it is not able to explain the fine structure. And another aspect I discussed that this alkali atom, I think I discussed earlier that alkali atom, its spectra is similar to the hydrogen spectra. Why it is similar, that I have explained you that in outermost cell it is one conduction electron, and other electron basically seal the nucleus, and so one can think that this it is like hydrogen atom of one electron, outermost electron, and the resultant this nuclear positive charge is screened by the outer electrons, and effective positive charge is it's close to 1 like hydrogen, or it varies basically depending on the screening. So, in case of alkali atom, say let us take sodium. So, sodium have 11 electron. So, outermost electron is in n equal to 3. So, for sodium, if I draw this energy level n equal to 1, n equal to say n equal to 2 and n equal to 3, I think, okay, n equal to 3, I should draw this. I need so if I take n equal to 3, okay. So n equal to 1, n equal to 2, n equal to 3, okay. So this this outermost electron is basically at here, okay, and these two are filled. These two are filled for sodium, 2 electron, and then this is 8 electron at n2 equal to 8 electron. So 10 electron. So 11 is having 11 electrons. So outermost electron is this one, and this 10 electron is screened. It screened the positive charge, 11 positive charge. So effectively, it's so this outer electron will see this positive charge is close to 1, plus 1 charge, plus E charge. Okay. So then it's similar to hydrogen atom, and then this energy for a hydrogen atom, this energy expression can be used for sodium also, where one has to replace Z. Is not 1, it is generally people write Z minus sigma, okay. Z equal to, one can replace Z by Z minus sigma. Sigma is called screening factor, screening constant. So Z minus sigma, it's close to, it's I think for sodium atom, its sigma is 7.4 kind of things. So it's not effectively it's 1, it's around 2.4 kind of positive charge. So anyway, for that there will be shifting of the energy levels, but nature of the energy levels means their discreteness and their transition will not be affected. So now this electron, so there is a possibility to jump at higher levels, n equal to 4, n equal to 4, n equal to 5, okay, n equal to 5, n equal to 5. Then n equal to 6, okay. So this 1, 2 is not effectively will not participate in transition. So let me drop it, So these are just from Bohr model, one can draw energy levels like this, but separation of energy level, of course, it will decrease, but here it is not, I have done, it is not in scale. So this now this Bohr Sommerfeld theory, whatever the energy expression we have got, so that also should valid for this alkali atom, okay, because it is similar to hydrogen atom as I mentioned. So what will happen? So now depending on k value, this energy level will split as we have shown here. So here you can see this n equal to 3, it will be split into 3 energy level, okay, this is one, and then second one say this, and say third one is say like this, okay. So that one will be k equal to 1, k equal to 2, k equal to 3, okay. So similarly, these energy levels also will split. So for 4 say like this. Similarly, others also split. So, this one will be k equal to 4, 3, 2, 1, 4, 3, 2, 1. Okay. So, this as I told, this k equal to, so this in principle I can write this one is SPD, SPDF like this. So, if I just plot in slightly different way, that so this also they will also split, you know, this. So, one should 5 lines, one should say 5, this on how many 6 lines, okay, 1 2 3 4 5. So, one has to, so it cannot be higher than this cannot be higher than this. So, it can be equal, so in between it should accommodate 6 lines, 6 energy levels. So, that way it will split it. So, each one will be splitted into orbital SPD, F, GH. Okay. So, if I just if I plot just S level, P level, D level, F level, F orbital, SPDF. Okay. So, I think I should write with small letter D, P, S. Okay. Now, here for n equal to 3, there will be 3 orbitals SPD. So, energy of S, if I plot here, energy of S is here. So, I think you can see energy of S is here. Okay. Then for P it is up, then for P it is up like this, then for D, so it will be like this. So, these 3 orbitals for basically n equal to 3 lines, if I just extend it. So, for n equal to 3, so these 3 orbitals. Okay. Similarly, for n equal to 4, I will get SPDF. So, if I plot SPDF, so S, yeah, and sometimes its energy is penetrate also inside of this one. So, it's for S line is I think it's, if I plot like this, then for P just above it, for P it will be above it, then D it will be above it, and then F, then I will get F. So, its energy level is basically for n equal to 4, Similarly, you will get for n equal to 5, n equal to 6, one can draw. If I do not draw more, so this what we are seeing, this lines for n equal to 3 below, and this n equal to 4. So, here if I consider transition following the rules del k equal to plus minus 1. So, there are 4 series, as I mentioned earlier, one can experimentally we see 4 series for alkali atom. What are those 4 series? It is principal series Np to say N0s. Okay. If this transition gives the series is called principal series. principal series, and then in S to N0 P, it's this transition gives the series is called sharp series, and then Nd to N0 P. Okay. So, this transition gives this its principal series, sharp series, and this called diffuse series, and another one Nf to N0 D, transition between these two, it gives another series is called fundamental series. Fundamental series. Okay. So, these are these 4 series observed in alkali atom. Here for all alkali atom one can see. So, here we have considered sodium. So, and these series are similar to the hydrogen atom series, means the separation between the spectral lines decreased and up and it goes towards the series limit. Okay. Whatever we have seen for Balmer series, Lyman series, here also similar series we observe. So, so now this series here you see this P to S, because this, or S to P, because this selection rule del K equal to plus minus 1. So, according to that, this transition only allowed, these transitions are allowed. Okay. And so, these all lines here are P lines, here all are D lines, D energy levels, here F energy levels. Okay. So, I should draw more to show series. I should draw more here. I think I can. So, I will write later on. So, now for this one n equal to 5, again we will get I think that and then this is F, this is D, we will get D, and then we will get V, and then we will get S. Okay. Similarly, n equal to 6 also. So, I do not need higher one. So, there are 5, but here I have drawn 4 S P D F. So, here also F. So, n is higher. So, these are becoming negligible. So, difference from is not deviated from n equal to 6 energy level. So, okay. So, these are S, P, D, F. Okay. So, to show the transition I need more lines. So, that is what I have done. So, now you consider that it's, you see, it can be any n, and any n0. So, n and n0, it is not necessary to be same. It may be same, it may be different, but main thing is that P to S. So, this is the line P and this is the line S. So, n0, that means this target from different higher lines, higher energy levels. So, it will jump to the just lowest one. So, here you can see this is S line, this is S line. So, from this P to S, so this transition is allowed, okay. Then this transition is allowed, so this transition, all from all P levels there is, so it will. So, you see, this is the energy difference, energy becoming higher, wavelength will be smaller. So, it is becoming smaller, and then it goes to the wavelength limit. Okay. So, it will form a series, So, if I just show here, if I show here this series, okay, and okay. So, here 3 lines I have done. So, these lines wavelength are smaller and smaller. So, basically you will get series, okay. So, it is the series limit as if like hydrogen series. So, this series is called principal series. Now, then S to P. So, this is the lowest P level, okay. So, now from S, higher S it will jump. So, these are the S lines. So, from here these S lines to it will one can. So, this will be the one transition, then this will be the another transition, this will be the another transition. So, this will be the transition. So, this way you will get transition, and again similar series you will get, basically it's and then series limit. Okay. So, this series limit will be this sharp series. Similarly, another series D to P. So, these the D lines, D energy levels, and this the P, lowest P is this one. So, I will get transition this, I will get transition this, I will get transition this, etc. right. So, again this wavelength will decrease towards, so I will get another series and then series limit. Okay. And then another from F to D. So, this is the F energy levels. So, to D, so this is the lowest D. So, lowest one we have considered N0. Okay. So, here N0 is for all cases is 3 and N are different. So, you will get transition, this is allowed transition, this is allowed transition, this is okay. So, you will get another series which is called fundamental series, here also similar way you will get. Okay. Okay. So, it is similar to the series of hydrogen atom, and that is the how these series are coming. So, it was not possible to explain from the Bohr expression, energy expression, but from Bohr Sommerfeld expression now we can explain the series. So, this in some extent this is the success of Bohr Sommerfeld theory, and in case of hydrogen also it is not 5 lines, but at least 3 lines we are getting. So, in some extent it is also successful, but it is there is a problem. So, this line from 3P to 3S transition, this is 3P, this is 3P. So, 3P to 3S, this transition 3P to 3S, this transition, this yellow light is very bright light and very famous light in laboratory. So, it is called D lines, it is called sodium D lines. This line is called sodium D lines, okay. And its wavelength is I think 5893 angstrom, 5893 angstrom. Yeah, most probably, I think so. Yellow light 5893 angstrom. But when it is observed in higher in microscopy of higher resolution, in spectroscopy of higher resolution, then it is observed that this sodium D line, it is not a one line, it is basically two line, sodium D1 and sodium D2 lines. Sodium D1 and sodium D2 lines, these lines is not a, so these are D lines, D line, and this line is not a single line, it is basically it's two lines, okay. Wavelength of these two lines, one is 5890 angstrom and another is 5896 angstrom, okay. So, average is basically 5893 we write for sodium D lines. So, sodium D lines is basically composed of two lines which are the separation is the 6 angstrom, and that was not observed earlier, but in higher resolution of spectroscopy. So, it was found that these are two lines, okay. So, but why, what is the origin of two lines, that cannot be explained from this Bohr Sommerfeld energy expression. So, this is one indication that whatever line, now we are getting more lines, but still it is not sufficient, and it cannot explain the say origin of this this D1 D2 lines. It cannot explain the fine structure of sodium H alpha line. It is how it is composed of 5 lines. It cannot, so here so far it cannot explain the origin of Zeeman effect when applied electric magnetic field. So, each line is splitted into 3 lines in case of normal Zeeman effect, but in case of anomalous Zeeman effect for weak magnetic field, so is splitted into even more lines. So, from where these lines are coming, so that was not able to explain. So, now that people started to think about the more quantization, so that in last class I started to tell you that about the another quantum condition was applied, the space quantization. So, I will discuss in next class. Thank you.